Now, concerning the cylindrical components, we're actually talking about the transverse and radial components. One needs to make use of this coordinate system whenever information about the angular motion is available. So whenever in the problem statement you see values like theta equal, theta dot equals, or theta double dot equals, you should directly assume a cylindrical coordinate system. Another case in which you would assume a cylindrical coordinate system is when the motion can be nicely described by a translational and rotational component. And the third condition, or the third case, is when you're simply given r as a function of time and theta as a function of time. And if you remember from the previous chapter, we said that whenever we're given parametric equations for r and theta, we can simply take the derivatives and find the values for r dot, r double dot, theta dot, and theta double dot. So it makes sense for these three cases to make use of the cylindrical coordinate system. Now, what would actually be the three equations of motion for the cylindrical coordinate system? Well, let us start again with the initial equation. Sigma f is equal to ma. Next, we can split that into the three axes, as we can see on the image on the right. So we get sigma fr equals to ur plus sigma f theta equals to u theta plus sigma fz equals to uz, and all that is equal to m times ar ur plus a theta u theta plus az uz. Now again, if we split the different terms based on the components, the vectorial components, ur, u theta, and uz, we'll end up with three different equations. Sigma fr equals to mar, sigma f theta equals to ma theta, and sigma fz is equal to mz. So we have now three different equations. How do we solve problems in cylindrical coordinate systems? The steps are exactly the same. Again, you select a coordinate system, you draw the free body diagram, you draw the kinetic diagram. Remember, drawing these two diagrams would actually help you understand more the problem and see clearly what the problem is about. And finally, you identify the different unknowns and solve for the variable you're actually looking for. Remember, the number of unknowns need to be equal to the number of equations for you to be able to solve the problem. Again, most of the time you'll have to make use of the kinematic equations, and that's because we have specific equations for AR, A theta, and AZ. So if you remember from the previous chapter, we said that AR is equal to R double dot minus R theta dot squared. A theta is equal to R theta double dot plus 2R dot theta dot. And again, as we've seen before, the way to go to calculate R double dot, R dot, theta dot, and theta double dot is to make use of the two methods we've discussed before. The first one makes use of parametric equations for R and theta and simply takes the derivative, while the second method actually represents R as a function of theta and applies the chain rule to calculate R dot and R double dot. So again, it is important to remember that in the case of the normal and tangential, or in the case of the transverse and radial, you will almost always make use of the kinematic equations to solve your problem. So you would make use of the kinematics and the kinetics equations to solve your problem.